so this insulating solid sphere. Now, why is the whole insulating bit important? That means that the charge cannot be conducted. So that means that wherever the charge is, it's stuck there. And that's important because it's uniformly distributed throughout the circle or the sphere. So if we imagine a sphere, okay, if it were an conductor, all the charge would reside on the surface. But since it's an insulated or insulating, we have stuck some charge in here. I'll make them blue maybe. So our charge, and pretend like I can make these uniformly distributed. So that means as we go out from the center of our sphere, we're capturing the same amount of charge in every layer. The density is the same. So this is the same symbol that we use for mass density, okay? But this density is charge per volume, okay? So just think about it that way. Okay, so we want to calculate the magnitude of the electric field at the point outside the sphere. So this sphere has a radius of A, but we want to calculate the electric field somewhere out here, some distance r away from the center, so that's r. Now, to use Gauss's law to make this super easy, because otherwise it's ridiculously hard, we can draw a Gaussian surface around this sphere. So imagine you can put a bubble around the sphere of charge. That's called the Gaussian surface. I usually abbreviate it GS. It's my Gaussian surface. Now, Gauss's law says that the charge enclosed by the Gaussian surface divided by epsilon naught is equal to the closed integral of the electric field dotted with the area that is perpendicular. That's the fancy way to write Gauss's law out. All right, so if our Gaussian surface is outside our total charge is Q, then how much charge have we enclosed? Some of it, all of it, none of it? All of it. So the charge enclosed is just a big old Q. That's lovely. And because our electric field is pointing straight out, okay, our electric field is pointing straight out. As it passes through this little bit of area right here, the vector that's perpendicular to the area is also parallel to the electric field, so that makes this dot product just a product of the electric field times the area. Now, what area? This electric field is all over the place, so it's pointing in every single direction. So what's the total area that that electric field is going through? The area of a sphere, right? So then this would be the product of E and 4 pi r squared. So it looks like a really awesomely wicked integration, but we are simplifying it because we're going to do things that are symmetrical. And it's going to be so easy. And later someone will teach you how to do this the wicked hard way. Okay. All right, so now we can solve for E, right? So the electric field looks like it would be, let's see, Q over 4 pi epsilon naught r squared. Does anybody know what this 4 pi epsilon naught looks like? 1 over 4 pi epsilon naught is K, right? K Q over r squared. So this is where the electric field anywhere outside this sphere behaves as the electric field of all of that charge if it was just concentrated at the center, which was on the mechanical universe video. Just like the gravitational field outside the Earth behaves as if all the mass of the Earth was concentrated at the center of the Earth. Okay? So that just kind of proves the electric field of a point charge and the electric field of a sphere with uniform charge density would be the same.